Okay, it's time to make some comments and talk about some connections. So, first of all, what does Green's theorem, specifically the vector form of Green's theorem, say if you have a vector field, two-dimensional vector field, f, which is p comma q, and this vector field is conservative? Well, let's write out the vector form of Green's theorem that we just saw. So line integral over a closed curve C. So C is a closed curve, counterclockwise. We have f dot dr, and then what we had just seen presented was that we could write this as double integral of curl of f dotted with the k vector dA. Well, the point is, if you have f as conservative, then curl of f is the zero vector. So then when you dot the zero vector with the k vector, well, then you get the zero scalar, right? So you end up right here integrating the scalar 0. So that means that the integral over this closed curve of f conservative gives you 0, but that's what we expected. We had previously seen that if you integrate a conservative vector field over a closed curve, you ought to get the scalar 0. So Green's theorem can compute a lot more situations, but we're actually just seeing that as a special case of it, you get something that we knew for conservative vector fields. Now, we're going to do something rather strange and get what some calculus books call another form of Green's theorem. So please keep track of the original Green's theorem. In fact, let's write it down right now. So in the line integral over a closed curve C, so that circle around the integral sign just to mean closed curve C. Okay. So in the integral of p dx plus q dy equals double integral over d of quantity partial derivative of q with respect to x minus partial derivative of p with respect to y dA. So this was the original Green's theorem, right? This is the scalar form of our original Green's theorem. What we're about to do right now is we're just going to make some algebra style replacements. We're going to replace each p that we see above, p above, with a negative q. We're also going to replace each q that we see above with just a p. Okay, and then we're going to compare what we have. I know this is going to seem a little strange, but we're just going to be very literal about this. So we're going to, in fact, I'll write this integral sign just directly underneath the integral sign that was here. So line integral over closed curve C, this p that's right here gets replaced with negative q, we still have a dx, plus the q that's above gets replaced with a p dy equals, and we'll have here double integral over d of the q that's here gets replaced with p, so we're going to end up with partial derivative of p with respect to x, and then there's a p here that's going to get replaced with negative q, but there's a minus sign in front. So how about we just bring the minus sign in front of the derivative, and minus minus will be a plus. We'll have partial derivative of q with respect to y dA. Okay, so this is another, well, let's actually just rewrite this ever so slightly. Apologies. Let's just write line integral over C of p dy. We're just going to switch the order of terms, minus q dx. Again, maybe we should have slowed this down over here, so let's actually redo this. Sorry, just to make sure. So there was a minus sign here originally, yeah, and then if we have derivative of, and then p got replaced with negative q, then on the other side here we can take a moment to clean this up as partial derivative of p with respect to x. The minus ends up being a plus now. Yeah, so a plus derivative of q with respect to y dA. This right here is what some books present as a second form of Green's theorem, or perhaps in some cases a first form of Green's theorem. But we should point out a couple things about how this sort of second Green's theorem is written. Okay, I'd like to point out that right here, this partial derivative of p with respect to x plus partial derivative of q with respect to y, if you had capital F is a two-dimensional vector field, capital P, comma, capital Q, this part right here, the integrand on the right side, that happens to be the divergence of the vector field. I mean, divergence is the way we had just defined it, right? So we actually just end up with a double integral over d of the divergence of f dA. And then on this other side, this right here, while it looks rather funny to write it this way, this will end up being the line integral over c of f dot a certain vector called n ds. We're not going to dig into some of the details right now, other than just to say that this is just a connection to something we're going to take a look at a little later in a future section. I'm just trying to preview some of the ideas, so don't worry about too many of the details right now. I just want you to get used to it. But this n is actually called a normal vector to the curve C, and then the entire integral on this side actually goes by a name. This is called the flux of the vector field F. For now, don't worry about it too much. We'll just say that let's try to describe what flux is in general. The general idea behind it is if F is, current of water again, water current, okay, then how much water leaves by going through C. That's the general idea behind what's going on here. The key point is, perhaps for now, don't worry about it too much, but just as a preview, if you look at a later section in the book, I'd like you to compare this theorem circled in blue. Again, it's really just a vector format of the second Green's theorem, but I'd like you to compare this with what the book calls the divergence theorem. And look at how similar the notation is.